Let's start with a really simple but also really profound question. Everything around us is made of stuff. But what happens if you take a piece of that stuff and you keep breaking it down smaller and smaller and smaller? I mean, where does it end? What are we at the very, very bottom actually made of? Well, today we're going to take a journey to the center of a particle to find out.
So let's just pick one, the electron. It's kind of the particle that powers our entire world, right? It flows through every single wire, every gadget we own. We've known about it for over 100 years. So you would think, by now, we'd have a really simple answer to this question. What is an electron made of?
For the longest time, the official answer has been, well, nothing. An electron isn't made of anything. It's a fundamental, indivisible point. It just is. But you know what? That beautifully simple answer, it hides some incredibly deep, complicated problems. And now some new ideas are starting to shake that century-old foundation, forcing us to ask, have we been wrong this entire time? Okay, so to really get why this is such a huge deal, we have to start with the reigning champion of physics. This is the theory that has totally dominated our understanding of the subatomic world for decades.
This is it, the standard model of particle physics. And let's be clear, this theory is one of the most successful things humanity has ever created. Seriously, it's our rulebook for the particle zoo, neatly organizing everything into families like quarks and leptons. And right there, in that rulebook, it says the electron is elementary. Translation, it has no smaller parts. It's the end of the line. And this isn't just some wild guess. Physicists have spent decades smashing particles into each other in these giant colliders. You smash a proton, and you can see the quarks rattling around inside. But when you smash an electron, nothing. You just see a single hard point. They've tested this down to ridiculously tiny scales. So, it seems settled, right? The electron is a perfect dimensionless point. Case closed. Well, not quite, because it turns out that in the weird world of theoretical physics, a perfect point is maybe the most imperfect, problematic thing you can imagine. It creates these paradoxes that have been giving physicists headaches for a very long time. Just think about it for a second. If you take all the mass and all the charge of an electron, and you cram it into a space that has zero size, its density becomes infinite. The electric field at its center becomes infinite. The math just completely breaks down. It produces nonsense. So how have physicists been getting around this for the last 100 years? They came up with this brilliant mathematical trick called renormalization. It's basically a procedure that lets you just subtract the infinities from your equations to get the nice, finite answers that match what we see in the real world. It works like a charm. But it's always felt a little bit like sweeping a huge, infinite mess under a mathematical rug. It kind of hints that maybe the whole problem is our starting assumption, the point particle itself. And then there's this little guy, alpha, the fine structure constant. It's just a pure number, roughly 1 over 137, that sets the strength for basically everything electromagnetic. The standard model needs it to work. It relies on it completely, but it has zero explanation for why it's this number and not something else. It's like a magic number that we have to measure in an experiment and then just plug into the theory by hand. It's another huge clue that maybe we're missing a deeper level of reality. This is where the story gets really interesting, because new theories are starting to pop up, and they offer a totally radical idea. What if the electron isn't a point at all? What if it's actually a structure made of light itself? One of these is called structural electrodynamics, or SED, and it suggests that an electron is actually a self-sustaining, twisting loop of electromagnetic energy. Think of it like a tiny, stable knot of light. And in this picture, all those fundamental properties like mass and spin, they aren't just numbers assigned to a point. They actually emerge from the physical shape and motion of this structure. It's a dynamic, circulating field, not a static point. Now check this out, because this is where it gets really cool. This model has a beautiful way of explaining the weird quantum property of spin. Okay, so in the SED model, the photon's total angular momentum is conserved, but its energy doesn't go through both loops at once. It flows in a sequence, first through one loop, then the other. This means the total momentum is always split between the two parts. So whenever you try to measure it, you only ever see half of the total momentum at any given moment. Osh divided by 2. All of a sudden, this bizarre quantum rule has a real, physical reason behind it. And that, right there, is the real appeal of a theory like this. It's not just trying to describe what happens with a bunch of abstract math. It's trying to explain why it happens with an intuitive, physical picture. Now, of course, SED is not the only game in town. There is a much, much more famous theory out there that also gets rid of the point particle, but it does it in a completely different and maybe even more mind-bending way. You've probably heard of it, string theory, and its central idea is just so elegant. The Standard Model has this whole zoo of different particles, right? String theory says, no, hold on. There's only one fundamental thing, a tiny vibrating string. So an electron, a photon, a quark, they're all just the same string, but they're vibrating at different frequencies. It's like they're all just different musical notes being played on the same cosmic guitar. I mean, string theory is incredibly ambitious. It aims to be the theory of everything. It fixes the infinity problem by giving particles a minimum size, and it even includes gravity, which is something the Standard Model just can't do. But there's a huge catch. For the math to hold together, it needs at least 10 spatial dimensions, most of which we can't see. And maybe the biggest hurdle of all is that after decades of work, it still hasn't given us a single unique prediction that we could actually go out and test to prove it's right. So, where does that leave us? On one side, you've got the Standard Model, wildly successful but also incomplete and a little bit clunky. And on the other, you've got these really elegant, promising alternatives that are still unproven. This is the real, unsettled frontier of fundamental physics. Let's just boil this all down one more time. You've got the Standard Model, which says a particle is a perfect point, but it forces us to ask, why do we get these infinities and these unexplained magic numbers? Then you have a theory like SED, which proposes a structured field of light, but the big question is, can we ever actually detect that structure? And finally, you have string theory, which says it's all a vibrating string, but we're left asking, okay, then where are all the extra dimensions? You see, each answer just leads to another, even bigger question. And this is not just a debate for people with chalkboards. This is happening right now. Experimental physicists at places like the Large Hadron Collider are actively hunting for the answer. They're looking for what they call compositeness, any tiny clue, any deviation from the predictions that would suggest that these fundamental particles are indeed made of something smaller. And so we are left with this one massive question. Is the very fabric of our reality, at its most fundamental level, made of simple points, complex structures, or a grand symphony of vibrating strings? The answer won't just tell us what an electron is, it's going to tell us what our universe is. And right now, that journey to find the answer is still very much underway.